Hello everyone. This week we are going to talk about continuous quantum states. By this I mean, for example, how do you write the quantum states of a particle which is moving in the one-dimensional infinite line? So the particle can be in any position, not just any discrete position, but you might specify it by a real number, its position along the line. So, okay, as far as these continuous quantum states are concerned, we are only going to be talking about them this week. And the reason I want to do this is, is for a number of reasons. One is so that you understand how the formalism we have been looking at so far, which has been confined to discrete states, actually extends to continuous states. But also, this will allow us to understand a particularly simple model, which is the so-called particle in a box model, which we'll use as a proxy for an atom, or for the states of an electron in an atom. And so in this particularly simple example, which we'll solve completely, we'll actually understand how to implement a qubit as via the energy levels of an electron in an atom. The example that we started with. Okay, now in concrete terms, we are going to be talking about how to represent the states of a continuous quantum system. We'll talk about Schrödinger's equation for a free particle on a line, and we'll talk about the uncertainty relation to try to make sense of what position and momentum mean in this context. Now, in terms of how these two lectures are organized, Lecture 9, this particular lecture, is going to be done in an extremely informal style. So what I'll try to do is paint for you a picture of what a particle on a line looks like, what Schrödinger's equation looks like, why it looks the way it does, and where the uncertainty principle comes from. So some of you might find this a bit a bit disturbing, because it's going to be a picture and not precise mathematics. But do play along with me, and in the next lecture, in lecture 10, we are going to make many of these things much more precise. Okay, but I think it's actually useful to have this more general, intuitive picture to have a sense of why things are the way they are. Okay, one more comment, which is that for continuous quantum systems, the math gets much more difficult. We are just going to sort of, I'll try to sweep much of it under the rug, even in the next lecture. But of course, a little bit of it is essential to describe these results more precisely. Okay, so now one thing that might be useful for you is just to understand that much of this and the next lecture are for your background, for your understanding of the subject, to understand how what we are doing with discrete systems corresponds to continuous systems. Of course, it ends up being much more important for the extra segment we have in the Berkeley course, which is on how to implement qubits in the lab. Experimental realizations of quantum computing. This is a segment that I might add at some later time in a later offering, but so for now, this 2-lecture segment is sort of self-contained, and okay. So in terms of the actual things that you might that I'd like you to get out of this lecture beyond the picture, the things that you might want to keep. Which will actually be invoked in the assignments are first, how do you represent a continuous quantum state? And then, what are the corresponding observables? Okay, so these are sort of the basic things about continuous quantum states. And then the other thing we'll of course you should know by the end of this is what does Schrödinger's equation? What does Schrödinger's equation look like for a free particle on a line in one dimensional, in 1D? And the last thing is the uncertainty principle. Between position and momentum. So what are the position and momentum observables, and what is the uncertainty principle for these say? Okay, so these are the concrete things you might want to get out of these two lectures, but of course the lectures are going to be, they will have a lot more intuition in them, which is just for your benefit. Okay, so let's try to describe the state of a particle which is free to move along a line which stretches out from -infinity to infinity. So let's pretend for the moment that a particle is only allowed to be in one of a discrete set of states. So only on these particular points, the integer points from -k to +k. Okay, so this we of course know how to write. We would say that the state of this particle is given by summation superposition alpha sub j, where j goes from -k to +k. So it's on one of these 2k plus 1 points. And of course there's this normalization condition that this is a unit vector, which means that the summation of alpha j magnitude squared is 1. Okay, and for by a slight abuse of notation, we could even think of alpha sub j as psi of j. Okay. All right, and okay, what does this wave function look like? Well, what it looks like is it gives a complex amplitude for each of these points. So maybe maybe this complex amplitude might if it was real, you could plot it out, and perhaps it looks like that. Okay, so it gives you some sort of a function like that. Now, what do we do? Well, first of all, to think of this as if you want to think of this tending towards a continuous function, let's actually let these integer points not be 0 from -k to +k, but let's have it be -k delta to +k delta, so that the distance between two successive points is now some delta instead of 1. Right? So this is not 1, this is actually now delta, 2 delta, minus delta, minus 2 delta, etc. Right? So the distance between the points becomes we allow it to be variable, and we let delta tend to 0, and we let k tend to infinity. Okay, so now the picture that we get is this. So we have our infinite line, and now that our superposition, instead of being confined to these discrete points which are delta apart, it's now just a function from the real line to the complex numbers. So we just have some function which goes like that. Okay, so we have some function psi of x. Okay, so it's a function from the real numbers, from the real line to to the complex numbers. Okay, so for every x, which is a real number, you have a complex amplitude. Okay, so instead of this superposition, now what we have is what's called a wave function, psi of x. Right? It plays exactly the same role as this vector psi, except now it's continuous. You know, it's not just a k or 2k plus 1 dimensional complex vector. It's actually an infinite dimensional vector, right? So for every point x, you have a complex amplitude, right? So we have an infinite dimensional vector space, a Hilbert space, where each of these points x corresponds to an orthogonal direction in this Hilbert space. And then we have this normalization condition. So what would the normalization condition say? Well, it would say, the corresponding thing here would say that the integral of psi of x magnitude squared dx from minus infinity to infinity is 1. Okay, so what's another way of writing it? Well, this is just the integral from minus infinity to infinity of psi of x conjugate psi of x dx. Right, and this is 1. Okay, so a particle on a line is described by a wave function, which is a function from the real line to the complex numbers. It's normalized. It's normalized in exactly the same way. So the integral of psi of x squared dx is 1. Okay, so now that we understand what the state of a particle on a line is, let's pose the basic question that we want to ask. So the most basic question we want to ask is, suppose that we know that what psi of x is at time t equal to 0. So psi is now a function of both x and t. And so at time t equal to 0, the particle is anywhere on this line, but we know what the superposition is. Let's say we know it's actually a Gaussian, e to the minus x squared. Right? Psi of x at time t equal to 0 is e to the minus x squared, suitably normalized, where maybe that normalization, I don't know, it might be something like that. Okay, but it doesn't matter, it's some constant. So what is this? So what does our wave function look like at time t equal to 0? It looks just like it's a Gaussian, right? So sorry, I'm making a mess of it, but it's a symmetrical figure like this. And now this is a free particle on a line, so there's no potential, and we want to understand, how does psi of xt evolve with time? Okay, so in other words, we want to figure out for some general value of t, what does psi of xt look like? Okay, so we want to understand how this wave function changes as a function of time. Okay. But once we answer this question, we also want to answer a different question. So can we answer, what is the velocity of the particle at time t? How quickly is this particle moving? Okay. Or well, you know that in quantum mechanics we already talked about how if you measure the system at a given time, then you disturb the system. So how would you measure the velocity of the particle? Well, you know, normally, classically, what you would do is you would see where it was at time t, and then you'd see where it was at time t plus delta t, and you'd look how far it went in that small interval delta t of time, and you'd divide distance by time by delta t and get the velocity. Okay, but now in quantum mechanics, if you measure the particle at time t, it's, you've changed the state of the system. So how can you measure the velocity? So instead, in quantum mechanics, the quantity of interest is not velocity so much as momentum, right? Which classically is m times v. So if the mass is m and the velocity is v, then the momentum is m times v. And so, well, why is it that momentum can be measured but velocity not? Well, to measure momentum, you don't need to measure the position at two different points in time. So if you've ever played American football or rugby, then you know that the player who ran into you had momentum, not because you measured his velocity at two different times, but just from how much it knocked you out. So you can measure the momentum of a particle by just hitting it against a detector. Okay, so these are the sorts of questions that we are going to answer in the next couple of videos, but in a very informal style. Okay.